Just lucky. So I can type that. How does the grid regulate the number of regulate the brightness? So can we have Esther? Can you give us the answer?
Shall the reason why it is able to regulate the brightness? When the grid is made more negative, the fewer the number of electrons allowed to reach the anode and the screen.
Sorry, because I'm typing it. When the what?
When the grid is made more negative.
Yes, proceed.
When the grid is more negative, the fewer the number. The fewer the number of electrons allowed to reach the screen and the anode.
Allowed to reach the what? To reach the screen and the?
Allowed to reach the anode and the screen.
Allowed to reach the screen.
Anode.
Yes. The anode and the screen, because anode first, isn't it? And?
Yes.
While or what?
And then less negative the grid.
And the less negative the grid. Yes.
The higher the number of electrons.
The higher the number of electrons. Number of electrons reaching the what? Number of electrons reaching
the anode and the screen.
Yes, correct. The anode and
Chat, if I say
yes.
The more negative the potential of the grid, more electrons to the cathode.
Come again.
More electrons bounce to the.
The more negative.
The more negative the potential
of the grid.
The potential of the grid. More electrons bounce to the cathode, and a few go to the anode and the screen.
Okay, we can say the more negative the potential of the grid, more electrons are repelled back to the cathode. Isn't it? Yes, that is okay. More electrons are repelled back to the cathode, and a few are allowed to reach the anode and the screen. Do you get it? Hey, members, you have started muting. You have started muting. Members, are you getting me?
Yes.
Yes. So the more negative, the more negative the potential of the grid.
The more negative the potential of the grid.
The fewer the number of electrons.
The fewer the number of electrons
that are allowed to reach the anode and the screen.
That are allowed to reach
the screen. That is it. And the less negative the potential of the grid, the higher the number of electrons that are allowed to reach the anode and the screen. And you should know that since the brightness depends on the number of electrons, then it means that as more electrons are able to reach the screen, then the intensity of the brightness of the spot
increases.
All right. Now let us let me show you something else here, the time base. So the time base is just can I call it is a switch. The time base switch is a circuit. It is a circuit that is connected to the X plates. The time base is a circuit that is connected to the X plates and is used to move the bright spot on the screen horizontally. Are we together? So in this, I don't know whether you are seeing the definition here very well. You should know that the time base is a circuit. Spelling of circuit. Let me see. Where should I type? Let me type here and see. Circuit. Spelling of circuit is this one. Circuit. You see, that's the spelling of circuit. This one here. So this is a circuit connected to the X plates and is used to move the bright spot left and right, sorry, horizontally on the screen. That is the time base. Now, the time base has what we call the time base has what we call the linear sweep or the flyback. So what do we understand? I would say
to move the
it's here, you have it in the notes, to move the bright spot on the screen horizontally.
thank you.
Horizontally. Okay, so the time base has got, it is a special electrical circuit which generates a sawtooth voltage. Sorry, the other one was time-based switch. The other one was time-based switch that is connected to the X plates. That was time-based switch. And then time-base is the electrical circuit which generates a sawtooth voltage, which generates a sawtooth voltage, to a certain value and falls rapidly to zero. So when you look at this is what we call saw. This one here. This is saw. Something like that. That is saw. So this is what we call a sawtooth voltage. So a time base is an electrical circuit which generates this kind of voltage, sawtooth voltage. And it raises rapidly or steadily. So it raises steadily. You can see it is not a curve, it is just a straight line. So the voltage will raise from this point to that point steadily. Steadily it is rising. And then falls rapidly or in a shortest time. It falls back to zero in a shortest time. So we have this slanting line. This is where we have the linear sweep. This is where the voltage is increasing. So once the voltage increases, here the voltage keeps on increasing. It increases from here up to there, okay? Then once it reaches here, it falls back to zero. So at this point where it falls back to zero is what we call the flyback, So the time, sorry, the PD is connected to the X plates and causes the spot of the electron beam to move across the screen from left to right. This is what we call the linear sweep. So once we connect the time base to the X plates, we shall see the beam moving left to what? Left to right, left to right, left to right. If the beam is moving left to right, it means that now there is a voltage that is being generated. That voltage is what we call the sawtooth voltage. And when that voltage is being generated, the kind of steady wave that we have, that part is what we call the linear sweep. So the linear sweep is where we have the voltage being generated. And then the flyback is where the voltage drops back to zero. So they're saying that the spot returns to the left before it starts the next sweep. So it keeps on going and then coming like that, from left to right, left to right. So the spot, this is called the flyback. So the spot will go from left to right. Then all of a sudden you see it from left to right. Then all of a sudden left to right. You cannot see it coming from right to left. Why? because from right to left, that time is very small, shortest time you cannot see it. So it changes rapidly to left and then starts again. So you see the spot moving from left to right and then back again left to right like that. But remember that between left to right, we have what we call the flyback. The flyback is the shortest time through which the voltage drops back to zero, or drops back to the left. It's what we call the flyback. So I want to, I don't know whether it's time to show you that video, but let us first continue. They're saying that during the flyback, the control grid is automatically made more negative, thereby suppressing the brightness on the spot of the spot. So during the flyback, the grid becomes more negative. So if it becomes more negative, that means that it allows very few electrons to reach. So during the flyback, you will not see the brightness because the number of electrons reaching the screen have been reduced down by the grid. So you only see a straight line from left to right, And during the linear sweep, that's when we have the grid that its negative potential has been reduced. If the negative potential of the grid is reduced, more electrons can reach the screen. So that happens during the linear sweep. But during the flyback, just a few electrons are allowed to reach the screen by increasing on the negative potential of the grid. So that's what they are saying, that during flyback, the control grid is automatically made more negative, thereby suppressing the brightness of the spot. Okay, so we looked at the fluorescent screen and its purpose. We say that it's where the bright spot is formed. It is coated with, it absorbs the kinetic energy of those electron beams. Now, there's a question that they ask that states the energy changes that take place. So you see here that the coating on the screen converts kinetic energy into light energy. Which kinetic energy? This is the kinetic energy of the fast-moving electrons, the kinetic energy of the cathode rays. So the kinetic energy of the cathode rays is converted into light energy, and the light energy is the bright spot that we are seeing here. The bright spot is due to that energy which has been converted to light energy and produces a bright spot when electron beam is focused on it. Members, are you getting me? With my